So today we are going to perform the experiment with the help of potentiometer, and the aim of the experiment is we want to calibrate a voltmeter using potentiometer. Calibration means we want to see whatever the voltmeter is reading, how accurate is this. So obviously we are going to use an instrument which is more sensitive, having less least count with respect to the voltmeter which is going to be calibrated, and potentiometer is such instrument which is having larger sensitivity and smaller least count, and that's why we are going to use potentiometer for the calibration of a voltmeter. So what you are seeing here is the instrument. We are having a potentiometer, 10 wire potentiometer. I am going to show you in details. There are two rheostats, first rheostat and the second rheostat. There are two cells for the supply. First is this lead acid accumulator and second is this battery eliminator. These are the two supplies. Then there is a standard cell, Daniell cell, electronic equivalent of Daniell cell. Then we are going to have this voltmeter to be calibrated. Then we are having this galvanometer for finding the null point. And there are some switches, one-way switch, one two-way key and one-way key. That's all. So this is the potentiometer. You can see this potentiometer is 10 wire potentiometer. 1, 2, 3, 4, 5, 6, 7, 8 and 9 and 10 wires. This potentiometer may be a 4 wire potentiometer, it can even be a single wire potentiometer, but in this specific case we are having a 4 wire potentiometer. In this potentiometer, these are the 2 points. Any one of these can be taken as the starting point and the other can be taken as the ending point, but for the sake of taking clear reading, this point which is near to the scale is taken as the first point and point A, and this is taken as point B. So when we take the reading, obviously when we are dealing with the first wire, so this is the 0 of the first wire, and as we go on moving, we can move up to the end of the potentiometer wire. Okay, the end of the potentiometer wire. Here, from here we are moving 1, 2 and up to 10 centimeter, say 25, 50 centimeter and so on, and we can move up to this end. This end is the 100 centimeter end. So for the second wire, this end starts as 101, 101, 102, 110, 120, 150, and ultimately this point will be the 200 centimeter mark. So for reading of the odd wire, that is first, third, the 0 starts from here and the end is 100 or 300 or 500 or 700 or 900. For the even wire, this end is 200, 400, 600, 800 and 1000, like that. So this is all about the potentiometer. Now we move to the lead acid accumulator. This is the lead acid accumulator. You can see here, this is lead acid accumulator, and this lead acid accumulator is having 2 terminals. One terminal is marked with a red color. This is red color. Red color indicates the positive terminal. This one is the green color indicating the negative terminal. This is the place from where the electrolyte is filled, so need not open it. This is the positive terminal and this one is the negative terminal. So this is first supply. In place of the second supply, we are using a battery eliminator instead of a second lead acid accumulator. This battery eliminator is having this as the switch, on off switch. Then there are variation. You can take 2 volts, 4 volts, 6 volt, 8 volts, 10 volts or 12 volt supply. Because we are dealing with the 2 volt supply of the primary cell, so obviously we are going to take at the most 2 volts. So this is connected to 2 volt. Now it is also having terminals. This is the positive terminal and this one is the negative terminal of the battery eliminator. Then we are using rheostats. And here is the rheostat which I am using. This is the rheostat, you can see it. This rheostat is having three terminals. One terminal, first terminal at the lower bottom, second terminal in the second end bottom, and this one is the third terminal. This is the third terminal, that is variable terminal. The two terminals are fixed terminal and this is the variable terminal. Now this is the voltmeter which is to be calibrated. Again it is a DC voltmeter, so there is a positive terminal indicated by the red terminal and negative terminal indicated by the black one. Now this meter is to be calibrated. As I told you that the instrument is to be calibrated by more sensitive, or the instrument which is having less least count, less value of least count. So let us find what is the least count of this voltmeter, and then we are going to find what will be the least count of our instrument which is going to calibrate this voltmeter. So you can see here, this is a 0 mark and this is 0.2 volt mark. This 0 to 0.2 is divided into 10 divisions. So 0.2 is divided into 10 divisions. So one division will be corresponding to 0.02 volt. So the sensitivity of this voltmeter is 0.02 volt, and it can measure from 0 to 1 volt. This is 1 volt mark, 0.8, 0.6, 0.4, 0.2 and 0. So this is to be calibrated for the complete range, means we have to take the reading of 0.1, 0.2, 0.3 up to 1 volt. Complete range is always calibrated. So this is the voltmeter which is to be calibrated. Now this is the standard cell with the help of which the potentiometer will be calibrated. So this is a Daniell cell electronic substitute, as it is written here. It is the substitute of Daniell cell. So obviously it is going to give a constant potential of 1.08 volts across its terminals. So these are the positive, this is the positive terminal, this is the negative terminal of the electronic equivalent of Daniell cell. This is the on off switch to make the Daniell cell on or off. This is the fuse used for giving a proper AC supply to the instrument. So mind it, this is not basically Daniell cell, it is the electronic equivalent of Daniell cell which gives a potential exactly equal to the potential of a Daniell cell. Now this is the galvanometer with the help of which we are going to determine the null point. This is the positive terminal of the galvanometer, this is the negative terminal of the galvanometer, and this is the scale. It can deflect both sides up to say 50 divisions. This side 50 division, this side 50 division. If I want to find the null point, then this pointer must exactly get coincident with this 0 mark. So this is galvanometer. Now this which you are seeing is a two-way key. Two-way key means this is the central terminal. This central terminal can be connected to this extreme terminal, or it can even be connected to this extreme terminal. So the current can flow from this to this side or even this to this side. That's why it is known as the two-way key. Whenever I put this plug inside this, what happens? These two terminals are short circuited. So this central terminal is connected to this extreme terminal. Similarly, when I put the plug key here, then this central terminal gets connected to this specific terminal, and this way the second way is switched on. This is short circuited. These two terminals get connected by short circuiting. So this is the two-way key. I think that's all about the instrument which we are going to use in this process of calibration of voltmeter with the help of potentiometer. Now let us see the circuit diagram which we have to make for the experiment. And in this circuit diagram you can see point A, that is the initial point, starting point of the potentiometer, and you can see point B, that is the end point of the potentiometer. There are 10 wires in between. First wire, second, third, fourth, fifth, sixth, seventh, eighth and ninth and 10th. So 10 wires are there. This is the extreme end point. This is the starting point of the potentiometer. Now we are going to make the circuit, this circuit first, that is known as the primary circuit, and whatever be the experiment, the primary circuit of potentiometer remains same for all the experiments. What I see is this first point, initial point, is connected to the positive terminal of battery E1, source E1, power source E1. The positive terminal of E1 is connected to point A. The negative terminal of E1 is connected to the extreme point of the end point of the rheostat, and second end point of the rheostat is floating, it is not at all connected to anything. Variable point, that is variable point, is connected to key K1, and from K1 it is connected to the second point of the potentiometer. I am repeating it again. The positive terminal of the battery, first battery cell E1, is connected to the positive A terminal. The negative terminal of the battery is connected to the N terminal of the rheostat. Second N terminal is floating, not connected to anywhere, and the variable terminal is then connected to one point of the key K1, and second end of the K1 is connected to point B. Now you can see this is point A of the potentiometer. It is connected to the positive terminal of the battery. See, this is the positive terminal of the battery. I am connecting it to the positive terminal of the battery. So positive terminal connected to point A of the potentiometer. Then the negative terminal of the battery, see this negative terminal is getting connected to one extreme point, this extreme point of the rheostat. There are two extreme points, first extreme point and second extreme point, and there is one variable terminal. This terminal is the variable terminal. So the negative terminal of the battery is connected to extreme. Then the second extreme point is floating, as I told you, this is floating, not connected to anywhere. This variable terminal is connected to one point of the key, one-way key, and second end of the key is connected to point B, that is the end point of the potentiometer wire. So this is the primary circuit. Now in the secondary circuit, the supply is this, and as you can see in the circuit that the positive terminal of this supply goes to point A. Positive terminal of this supply goes to point A. As I told you, this is the secondary cell, secondary power supply. The positive terminal of the secondary power supply is connected to point A. Positive terminal of the supply is connected to point A. The negative terminal of the supply goes to one-way key, and from one-way key it comes to the second end of the rheostat. First end is connected to positive terminal or it is connected to A. Either you connect it to the positive terminal of the battery or you connect it to point A, both are the same thing. So positive terminal of the supply connected to point A, one extreme terminal of the rheostat connected to point A, second extreme terminal of the rheostat is connected to the key, one-way key, and through one-way key it is connected to the negative terminal of the battery. The variable terminal goes to two places. The variable terminal goes to the negative terminal of the voltmeter, which is to be calibrated, and the second end goes to the second extreme of two-way key. This is two-way key, central terminal, one extreme terminal, second extreme terminal. Okay? So many things are connected to point A. Number one, the standard cell's positive terminal is connected to point A. The positive terminal of the voltmeter is connected to point A. One extreme terminal of the rheostat is connected to point A, and positive terminal of the secondary battery is connected to point A. All these four are connected to point A. Negative terminal through a key connected to one extreme of the rheostat, second extreme of the rheostat. The variable terminal goes to 2.1 point is the negative terminal of the voltmeter which is to be calibrated, and second is the second extreme terminal of the two-way key. The negative terminal of the standard cell goes to the first extreme terminal of the two-way key. The central terminal of the two-way key you can see is connected to galvanometer, and through galvanometer it goes to the jockey. So that much is the secondary circuit. So as I told you, the secondary source, the positive terminal of the secondary source, this is the positive terminal. The positive terminal of the secondary source is connected to one extreme of the rheostat, and the same extreme is connected to point A of the potentiometer. Agreed? This positive terminal of the secondary supply is connected to one extreme, and the same one extreme is connected to point A. So both positive terminal of the battery and one extreme terminal of the rheostat, both are short circuited and connected to point A. The negative terminal of the battery, this is the negative terminal connection, this is negative terminal, this is the wire connecting this to one end of the one-way key. The second end of the one-way key, it goes to the next extreme of the rheostat, second extreme of the rheostat. So this is the connection. Whenever I put this key, the secondary circuit comes into the connection, and if I put out the plug, it is switched off. Now we have to connect the extreme, that is the terminal, that is variable terminal, with the circuit. Now first we have to calibrate the potentiometer wire itself. Means before using an instrument, we have to calibrate that instrument for the calibration of other, and that's why the potentiometer wire is to be calibrated first. And for that, what we do, we put the plug key on K1, that is the, we are switching on the primary circuit. So this is the plug key I have put for making the primary circuit in connection to the potentiometer. Now because this is to be calibrated with a standard potential, and that's why I switch on this standard cell. This standard cell is now switched on. Now that standard cell is providing a definite potential of 1.08. Now my aim is, I want to drop that specific potential across the complete length of the wire, and for that what I am going to do is, let us have the galvanometer in view. Now I put the jockey in the point A, that is first extreme. You can see it very well that the galvanometer gets deflected towards left hand side. When I put to the next extreme, that is point B, the galvanometer is again getting deflected in the same direction. Now I vary the potentiometer, that is the rheostat, I vary the rheostat in such a way that the deflection at B becomes equal to 0. So I am varying the rheostat here. I am moving it towards the one side, and I see the deflection in the galvanometer. You can see that the deflection has diminished and it is approximately near 0. Now I put this at the end, at B point, and I slide the rheostat. You can see the reflection, the reaction. See, I am sliding the rheostat, and because of sliding, the galvanometer's deflection becomes in the two different sides of the reference. Now by varying this the rheostat, I try to bring the needle at 0 deflection. I want to bring it to 0 deflection, and when this happens, my jockey is at point B, means I have taken the complete length of the potentiometer wire, and I have adjusted the rheostat RH1 in such a way that there is no deflection in the galvanometer. This condition states that the complete potential of the standard cell, that is complete potential of 1.08, it drops across the complete length of the wire, and the complete length of the wire is 100 centimeter. 1000 millimeter, sorry, 1000 centimeter. Okay, 10 wires, one wire is having the length of say 100 centimeter. So obviously 10 wires are going to have the length of 1000 centimeter. So the complete potential of 1.08 is distributed equally in the wire, because the potentiometer wire is having uniform diameter. So each unit length of the potentiometer wire is going to have the same resistance, and because it is same resistance, so equal potential will be distributed. So 1.08 potential is distributed in a length of 1000 centimeter. So obviously 1 centimeter of this potentiometer wire now corresponds to 1.08 divided by 1000 centimeter volts, this much volts. Now the calibration of the potentiometer wire is over. Now because this standard cell was only for the calibration of potentiometer wire, now I switch off this Daniell cell, that is standard cell, permanently, and the key which is connecting this to the circuit, that key is removed and it is never going to be placed again, because the Daniell cell has nothing to do with the calibration of voltmeter. It has only had a use to be calibrated to the wire of the potentiometer to be calibrated, so its work is over. Now we are never going to switch on the Daniell cell, and even we are not going to connect the Daniell cell in the circuit again. Now for the calibration of voltmeter, we are going to switch on the secondary circuit. For switching on the secondary circuit, we switch on the secondary supply. The supply is now on. We put the plug key to connect it to the circuit. So you can see we have connected, and now what we see is, you can see in the voltmeter there is deflection, and the voltmeter is reading around say 9.9, above than 0.9 potential, 0.9 volt potential. Now what we do, we vary this rheostat, secondary rheostat, and with the help of secondary rheostat we try to develop a potential of say 0.1 volt, and that is to be measured by the voltmeter. So now you can see this is 0.1 volt potential. If you want to see it clearly, I can show you. This is 0.1 volt potential. Is it visible? Okay. So now 0.1 volt potential has been developed. Now I want to see, the voltmeter is reading 0.1. What exactly is this potential? For that what we do, we use the second key of the plug of the two-way key for connecting the galvanometer with potentiometer wire. Now it is connected to potentiometer wire. Initially, when we put this plug key in the first hole, this secondary cell, that is standard cell, is connected. When we put it here, the galvanometer now gets connected. Now we want to find the balancing length for this specific potential of 0.1 volt. Now to find the actual potential, what we do is, we measure it with the help of this potentiometer wire. As I had told, that 1 centimeter of this potentiometer wire corresponds to 1.08 divided by 1000 volts. So I put it in the first wire, and the deflection is towards left hand side. I put the jockey in the second wire, the deflection is towards right hand side. Means the balance will be between the first wire and the second wire. So I go on moving the jockey to the different points of the potentiometer. See, I am bringing it here. Here again the deflection is towards left hand side, and in the right, the second wire, the deflection is towards the left hand side. Now I move it towards the extreme. I can see the deflection has reduced. The deflection has reduced in the first wire. Still it is in the left hand side. In the second wire it is towards right hand side. I move further in the first wire. So this is the first wire. The deflection is still less but not null. it is not null point. I go on moving it. See, I have moved it to the extreme point. So now I am very near to the end of the first wire, and you can see still the deflection is towards left hand side. Okay, so I move to the second wire. You can see this is the deflection in the left hand side. So obviously the last end of the wire will be approximately equal to null point. You can see here I am keeping it at the extreme end. I am keeping it at the extreme end of this, and if I move it towards end, I find that the deflection becomes equal to 0. This is the null deflection. This is the null deflection. So for this 100 centimeter is the reading for 0.1 volt. For setting 0.1 volt, the null point is at 0, that is 100 centimeter length. So first reading for 0.1 volt, the reading becomes equal to 100 centimeter. Rheostat to make the potential to be equal to 0.2 volt. See, I am sliding slowly to make it 0.2 volt. You can see now it is 0.2 volt. It is 0.2 volt. Again, for this potential we are going to find the balancing length. Now for 0.2 volt potential, I am putting the jockey in the first wire. You can see the deflection is toward left hand side. In the second wire, still the deflection is towards left hand side, although it has decreased. In the third wire, it is towards right hand side. So obviously the balancing length will be between the second wire and the third wire. So we again move to the second wire and we keep on moving towards the end of the second wire. Means we are moving from 100 to 200 centimeter range. Slowly we are moving and we are seeing that the deflection is getting reduced, and here you can see at this point the deflection is approximately equal to 0. At this point the deflection is 0. Okay, so this length, this position will be the position of the null point, and to find the null point's position, what we do, we keep a scale at that point, scale perpendicularly, and we find the length. Because this is 100, from here 101 starts, 102, 103, and what we are reaching is, it is approximately 190.5. It is 190.5. So the reading is 190.5 for the second potential, that is 0.2 volt, and so on. We keep on increasing the potential from 0.1 to 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and ultimately to 1 volt. And for every potential we have to find the balancing length. As you have seen, for the first potential, that was 0.1 volt, we got the null point at 100 centimeter. For the second, that is 0.2 volt, we are getting the null point at 290.5 centimeter. Similarly, for each and every potential we are going to get the null point, and then we are going to calculate the actual potential, and from actual potential and observed potential through the voltmeter, the difference will be the error. So we are going to get the error, and then we are going to plot the graph between the actual potential, that is the potential read by the voltmeter, and the error, and that will be the complete experiment. So let us move to the readings which has been obtained, and then we are going to go to the graph. Let us see the reading. This is table 1 for calibration of potentiometer wire. What we have taken, the length of the potentiometer wire corresponding to EMF of the standard cell. Obviously we kept the jockey at point B, that is last point. So the total length of the wire which was corresponding to the standard cell was equal to 1000, that is in centimeter. So it is 1000 centimeter. The EMF of the standard cell is provided. If it is Daniell cell, it is 1.08 volts. So it is 1.08. Now the potential gradient means fall of potential per unit length, is 1.08 divided by 1000, which becomes equal to 0.00108 volts. So this is the value of the potential across 1 centimeter of the wire. Now, the second table, table number 2, is for the voltmeter calibration. This is the column which shows the voltage as read by the voltmeter. This is the voltage read by the voltmeter. This is the balancing length of the potentiometer wire. So this length multiplied by potential gradient gives the actual potential. So the actual potential is here in this case, the observed potential in the voltmeter was 0.1 volt. The balancing length was 99.6 centimeter. 99.6 multiplied by 0.00108, it gives us a rounded value of 0.108 volt. So actual reading is 0.1. The observed reading is 0.108. So the error is 0.008 volt. This is the error for the first reading. Similarly, for 0.2, the balancing length was 189.8. For 0.3, the balancing length was 286. For 0.4, the balancing length was equal to 381. For 0.5, the balancing length was equal to 479. For 0.6, 577. 0.7, 672. 0.8, it is 783.5. 0.9, it is 865. And for 1 volt, it was 983.5 centimeter. We have calculated the corresponding potentials measured by the potentiometer. We have got the difference in the actual reading and the observed reading. Actual reading and the observed reading. This is the actual 0.934, observed is 0.9. 0.846, the observed is 0.8. Now, what we have to do is, we have to plot the graph between this the observed potential, that is potential as measured by the potentiometer, and the error occurring in that specific reading. That will be the portion of result of this specific experiment. Now see, the graph plotted between the voltmeter's reading and the error. You can see in the x-axis, I have plotted 0.1, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9 and 1 volt. So the voltmeter reading is plotted in the x-axis, that is independent variable, and the error is plotted in the y-axis. This is 0.010, 0.020, 0.030, 0.040, 0.050 and so on. So when I plot the graph, the basic difference, suppose the error is 0.008. So this is 0.008 for 1.1 volt. For 0.2, it has reduced to around 0.5. 0.3, it is around 0.01 volts. So I plot the points here, and then one by one I join the point. 0.1 potentials point is going to be joined with the 0.2 potentials point. Then 0.2 potential, 0.2 volt potential point is to be connected to 0.3, 0.3 to 0.4, 0.4 to 0.5, 0.5. Means it is 0.2 point curve. It is not a curve in which we look for a line, straight line, which is accommodating the most of the point. No, it's not like that. It is the 0.2 point graph. Means every point is considered and every point is connected with the next point. So this is the calibration curve. The calibration curve looks like this. So when you plot this, when you have taken reading and plotted this graph, your experiment is completed. So that's all in the experiment of potentiometer. I think you might have understood, and still if you want to know, you want to perform, you can come to the class and you can perform the experiment.